All right, so let's finish this. Will it go viral? So we got three equations here. So the first equation, so first off, we're starting at 10 p.m., right? And the first equation is we start with 3 people. Every 5 minutes, they're sharing it with 3 people. So this is definitely exponential growth here. We're starting with 3 people, but we're sharing it with 3 people. So what's our rate? We go from, like if it's just me sharing the video with 3 people, I go from 1 person to 4 people, right? So this is a 400% rate, but this is happening every 5 minutes. So our time is divided by 5, right? And then how long does this happen? This happens until 10:20. So we would plug in 20 minutes, right? And when we plug in 20 minutes, put that in a calculator, right? And we should end up with 768. Okay, so 768 people see it. Okay, now let's move to the next one. Over the next 4 minutes, right, 30 people discover the video, right? And this continues. Every 4 minutes, 30 people discover the video. So 30, 30, 30, that's linear. So MX plus B, right? So what's our slope, our rate? It's 30 people every 4 minutes. So that's 30 divided by 4. You should get 7.5 people every minute. And then our starting point is where we left off, this 768, right? And so then we go, okay, how many minutes did this happen? This happened from 10:20 until 11:32. Sometimes I don't know why it does that, right? 11:32, right? So how many minutes is this? 72 minutes. So we would plug in 72 minutes. Right, and when we plug in 72, we will now get to 1308. So we're now at 1,300 people have seen the video, right? And then so the last equation here, the late night show, right, shares it, and so now it is doubling. Okay, so we're back to exponential. It is doubling, right? So what's our start? 1308. That's where we're at. It is doubling. Okay, but it's doubling every 3 minutes. Now, again, how long do we have, right? To go viral, it said we had 2 hours, so 10 to 12, right? So we only have 28 minutes left. So we would plug in 28, right? And when you plug in 28, you get 843, 764. So did we do enough to go viral? Well, we had to get to 1 million, so no, we did not. Okay, moving on to 109. Okay, how many years will it take for our money to double compounded continuously? So continuously compounded interest is PERT. Okay, so P times E raised to the RT, right? And our principal is 1, and we want to double it, right? So 1 and 2, again, it doesn't matter what you start with. When you double it, when you're solving for these, it's 1, 2, right? So E is always E, and then our rates we have here, A, B, C, and D. So we'll start off with 0.05 times T, and we're just solving these, right? So basically we're going to end up with 2E to the 0.05 T. We will natural log both sides or change it to natural log. So the natural log of 2 equals 0.05 T, right? And then we just divide by 0.05, okay? And you would just continue this, natural log of 2 divided by 0.06, 0.08, and then 0.1 to get all these answers. Okay, you should be able to do that pretty easily there. Okay, E, financial managers use a quick calculation that does not involve logarithms to approximate how long it will take for your money to double. They call it the rule of 72. So determine the relationship between interest and this rule of 72 with your team. Determine the best number, round to the nearest. Well, so here's what we're saying here, right? Is it ends up being like that equation, right? So if we take the natural log of 2, so like if we're just solving this, okay? If we take the natural log of 2, you get a rate, right? Of like 0.69, but it's very close. And so what they do is they use 72 divided by x, and that is that r of x. That is that function to approximate the number of years it would take for your money to double, right? Given a certain interest rate, right? And again, this rate is different, but it's just, that's their rule of 72, just to keep them from, using logarithms. Okay, it comes out easier that way. So, a savvy financial investor might want to convince their customers that they know how to make their money double faster, right, with a more accurate calculation. Okay, well, again, if you look, it's not actually 72. It's actually, if you do the natural log of 2, right, it's actually 0.693. So you could use that. Again, what they do is, instead of doing a rate, they're putting in a whole number. So they would say 69.3, which is a little faster than 72, right, divided by that rate. So that would be their way of doing that, is to get it even closer instead of using 72. Okay. 110. So we got two best friends studying chemistry together. They have different professors, right? But their class uses this half-life formulas, right? So we have two different half-life formulas, right? And we're trying to explain why the two different formulas why there can be two for the same calculation, and discuss how they are related. So if we look here, one is E, right? And then one is, 1/2 to that power. So if we're looking at these two equations, which I'm going to write them down, right? So e to the negative t, natural log of 2 divided by h, right? And then over here we have n0. Then we have 1/2 raised to the t over h, right? So here's the deal. Okay, let's look at what happens when we have e, right? NOs are the same, right? We have divided by h, that's the same. We have a t, that's the same, right? So let's look at this e to the negative natural log of 2. Let's look at this, right? So what I would want you to do here is to put this in your calculator, right? E raised to the negative natural log of 2, okay? And if you do this in your calculator, guess what you get? 0.5, right? So it's actually the same as 1/2. So it's getting you to the same thing there. So again, that you can see how exponentials and logs and all this stuff can be related, and how you can use different things, but it was still the same as long as it's the same mathematically, right? And then the last thing here is just measuring intensity of an earthquake. So we have the Richter scale, which was defined as M equals the log of the intensity, right, over S, which is a standard earthquake, right, intensity. And so what's the magnitude, right, of a standard earthquake, right? So this would be the log of S over S, right, or just the log of 1 in that case, so a standard earthquake. So the magnitude is 0 of a standard earthquake, right? And then so B says, how do the intensities of 5.1 and 5.2 compare, right? So we're just plugging in the intensities, right? So we're plugging in this log of 5.1, right, over S, and then the log of 5.2 over S. Okay, so really what this is if you change this to exponential, right, what's the difference there? We're talking about 0.1, right? So this is 10 to the 1.1, and this would be 10 to the 1.2. Okay, and so what are we talking about there? So if you did this, right, like if you put this in 1.1, right, you're going to get 12.59, right? And if you did 10 to the 1.2, you're going to get 15.85, right? And so, what are we talking about, right? We're talking about intensity. How much bigger is that, right? So just divide the two, right? And you get around like a 1.25, which is about a 25% increase, right? So that little bit of that tenth of a point in intensity can raise the magnitude by 25%, right? So just kind of comparing how they relate to each other, right? So then the largest earthquake recorded had a magnitude of 9.2. What's the intensity of this earthquake? So 9.2 equals the log of I over S, right? Again, they give us this S, right, is 10 to the negative 4. So really this is like the log of I times 10 to the 4th, right, is really where this comes from. Okay, so we have 9.2 here, right? And then if we're solving this, right, what happens, right? So we're looking into this, right? So this is 10 to the 9.2 equals I times 10 to the 4th, right? If we divide by 10 to the 4th, you're just subtracting, right? So this is 10 to the 5.2, right? So you would then plug that in, 10 to the 5.2 in your calculator, right? And you're going to get that it's this massive, right, 158,490, so 489, right, in intensity, right? And so you can tell they're like very big intensity level. Okay. Awesome. So then, same deal here, looking at these earthquakes and how they compare. Okay, but I mean, you're solving, right? So you're going to have some of these. So you're going to have a financial problem on your homework, but you're going to go back to some of your base stuff, your log rules, those things like that. So this is concluding chapter 5.